Welcome to the third installment in our acids and bases unit. We're about midway on page 7, and this is when we're going to start talking about the pH scale and getting into calculations. Now, it's my hope that you've already been introduced probably broadly in first year chemistry to acid and base chemistry, but also more importantly, the pH scale. So really quick, this is a scale that essentially goes from, 0 to 14. And it's a way to specify the acidity of solutions, okay? And so we're going to define the pH as the log of hydronium or hydrogen ion concentration. And so really quick, I'm going to go ahead and highlight what I just said. And so we really can quickly see here that the pH scale is a logarithmic scale, bases of 10. I want to bring your attention further over to this visual here on the right side of your page. And if you take a look, this kind of outlines how the concentration of hydrogen ions relates to pH, okay? And so again, really quick, let's point out that if it is a pH of 7, which is what we call a neutral solution or something that is neutral, is going to have a hydrogen ion concentration of 10 to the minus 7. And you can see that as our numbers get smaller in hydrogen ion concentrations, that we're going to have more of a basic or alkaline environment. And you'll see that consequently our pH numbers will increase in value. And then consequently, the opposite is true. Our hydrogen ion concentration slowly increases logarithmically as we go down to something that's more acidic. And then that is going to correspond with smaller numbers. So it is true. Something more acidic will have a pH of less than 7. And something that is alkaline or basic will have a pH greater than 7. And one more time, if it is a pH of 7, it is neutral. Now, before we talk about how we can interchangeably calculate the pH using hydrogen ion concentration, or how we can calculate the pOH using the hydroxide ion concentration. And you can see here that that's the next equation that I just highlighted here. So we're going to be dealing with logs, you guys. You are going to need a calculator to do this. Just wanted to point out, though, just to show and highlight this logarithmic nature, that if you were, for example, to take a substance that has a pH of 4 and then, compare that to a substance that has a pH of 6. Well, if that's the case, and since this is a logarithmic scale, if a substance has a pH of 4, it's going to have 100 times more hydrogen ions in solution than that of the substance that has a pH of 6. Conversely, if you have something that is a pH of 5, it's going to have 10 times more hydrogen ions in solution than that of a substance that has a pH of 6. Okay. And so a lot of the times we really speak of the pH scale in terms of pH, but you can also speak of it in terms of pOH. And so there is a really important equation that you guys are going to use quite a bit, that if you take the pH of something and you add that to the pOH, then it should get 14. And of course, that is when we max out on our pH scale. Lastly, we learned in the last podcast with the ionization of water that the equilibrium constant for water, we also call that the autoionization constant for water too. So we designate that, remember, as Kw. And you can see here that that expression, let me erase this because it's kind of in the way, that expression is the concentration of hydrogen or hydronium ions times the concentration of hydroxide ions, at which point we would get the value that we learned about, 1 times 10 to the minus 14. Okay, really quick before we go any further, I want to show you your AP reference sheet, and let's take a look at what types of values and equations that are given to us here. I'm going to go ahead and in the equilibrium portion of your AP reference sheet is where you'll find the necessary items for acid and base chemistry. And you can see we have our Kas, we have Kb, we have Kw. You guys see that right here. And so notice Kw is also equal to Ka times Kb. All right. And so I'm going to go ahead and go back to our notes. And one of the things that you can just also add here under this area is Kw equals Ka times Kb. And I say that just because it'll help you with some calculations that are coming up here pretty soon. Another thing that you can do definitely is use this handy little handout. Again, you can't use it on tests or quizzes, but it's a good way to kind of get you to kind of visualize how we're going back and forth from hydrogen or hydroxide ion concentrations to pH or POH respectively, okay? And so anyway, we'll go ahead and put this to use in these equations here in just a second. But before we move on, let's talk about how we report sig figs when dealing with acid and base and pH problems, okay? It is different, all right? Now, these 3 bullet points here kind of overview and explain it, but it is not what you would think. Now, it's been a while since we reviewed sig figs. They're still super important. Now, in pH problems, it's going to be different. So let me just give you an example. If I am given a value, let's just say I'm given some molarities here. I'm given 1.15 molar versus 1.2 molar. And let's say that these values I'm going to use for calculations to go to pH or something like that, for example. Now, what you should see here is that in this first value, this is 3 sig figs, and in the second value, it's 2 sig figs, right? Well, when you're dealing with pH, what this would mean then, let's go back to the first one. Since this value here is 3 sig figs, you would need to report your pH to 3 decimal places. Okay, so I'm just going to give an example. Okay, that pH is going to 3 decimal places. And you guys, I didn't do any calculations here. I'm just making this up. The number anyway. Let's say I go to the second one and we know that 1.2 molar is 2 sig figs. Well, if I'm doing a pH problem, what that means is I would need to report my pH value to 2 decimal places. Again, I'm just giving you an example. 3.2 decimal places, okay? So it's a little bit different here on how we do sig figs and pH problems. Please practice it and then you will know it. Let's take a look at the top of page 8. There's a couple of exercise problems. And here you're going to use some of the formulas that we just went over for pH. Again, let's take a quick look at our AP reference sheet. I'm specifically talking about some of these formulas right here where you see the hand. Okay, you're going to use these right now to interchangeably go back and forth between hydrogen and hydroxide concentration and pH and POH. Guaranteed to see a couple of these types of questions on the multiple choice portion. All right, for exercise 7, I'm going to go ahead and do A and C for you. You can do B on your own. And it's saying calculate either the hydrogen or hydroxide concentration for each of the following solutions at 25 degrees Celsius, and go ahead and indicate whether the solution is neutral, acidic, or basic. All right, so you can see here, there's one thing I want to point out before you start. This is at standard temperature, 25 degrees Celsius. There is one thing on our AP reference sheet that we just also talked about that I'm going to jot down here. We learned that the auto ionization constant for water, Kw, is 1 times 10 to the minus 14. Okay, another way to think about that, again, this is also on your AP reference sheet, is that then the Kw is equal to Ka times Kb. And again, another way to think of that is the hydrogen ion concentration times the hydroxide ion concentration. Okay, knowing all of these things, that's going to help us do these problems. Now look at A. We're given a hydroxide concentration. So we know the concentration of whatever base this is. I don't know, but we know the concentration, and that is 10 to the minus 5. All right, and if our goal is to determine the hydrogen concentration, how do you think we go about doing that? Well, if you said we're going to use this formula right here, then you are spot on. So let's go ahead and rearrange this. We know what Kw is. We know what OH concentration is. So let's go ahead and solve for hydrogen ion concentration, which we would then put our ionization constant 10 to the minus 14 in the numerator, and then our hydroxide concentration, which was 10 to the minus 5. Okay. Now, when I do this, let me just go ahead and show the work. So when I lay it all out there, I get 1 times 10 to the minus 9 as my hydrogen concentration. So let me go ahead and jot that down here. Now, there's a couple of things that you can do. You could just look at what your the size of your concentration is to determine if it's acidic, basic, or neutral, or you can take these concentrations and plug them into, for example, pH, the negative log of the hydrogen ion concentration, okay? If you did that, you would find that the pH is going to be a larger number. Again, basic, above 7, pH is 7. So you can do that on your own. But what I did here is I looked at my hydrogen ion concentration, 10 to the minus 9. Now let's scroll back up. Watch your eyes there. Here you can see what I've done. I highlighted it in yellow on the scale over here on this image. And of course, that is a pH of 9 is basic or alkaline. Okay, I'm going to skip B like I said. Let's go ahead and look at C. Oh, look at that. They gave me the hydrogen ion concentration, which was 10 molar. Again, I'm going to go ahead and just rearrange the equation to solve for OH, or hydroxide ion concentration. And again, you would use this equation over here that I just drew an arrow to. Okay, and I'm going to go ahead and plug and chug. Don't forget, you know your concentration of the acid. It was given to you, so you know your Ka. Final answer for hydroxide concentration was 10 to the minus 15. Again, you can, kind of assess with that hydrogen concentration. Look at that big number. That is on the pH scale going to result in something very acidic. If you don't believe me, again, you could take the pH equation, the negative log, and take the negative log of 10. And indeed, you will find that it's very acidic. Exercise 8. We are here tasked to calculate pH or pOH. Look at this first one. Again, standard temperature, 25 degrees Celsius. It's telling us that we've got a hydroxide ion concentration. And you guys already know that we can actually find the pOH. Again, these equations are on your reference sheet. If you take the negative log of the hydroxide ion concentration, that will give you your pOH. And so let me go ahead and calculate that. You guys, I got a pOH of 3. Okay. Now, to get the pH, remember, and one more time, this is on your reference sheet. pH plus pOH is equal to 14, which is what our scale, our acid and base scale maxes out at. And so if we have the pOH, we can just rearrange this and solve for pH, right? So pH is equal to 14 minus 3, giving us an answer of an 11. So this is a basic solution. Why? How do I know that? When you're trying to determine acidity or alkalinity, always use the pH value. Okay, the pH is 11 and therefore it is basic. All right, so let's do B. We're given the concentration of some acid. So hydrogen ion concentration, you would simply just take the negative log of that, and you will find that you will get 0. Okay, again, to find out the pOH, you would simply just say 14 minus what you calculated for the pH, which was 0. Of course, that's 14. And so really quick, you're going to, one more time, use pH to help clarify what's going on here, if that works for you. You could use pOH too, you guys, but we always come from the perspective of the pH scale. And so if this is a pH of 0, this is a very acidic solution. All right, exercise 9. It's now asking us to calculate all kinds of stuff going on over here of a sample of human blood that's measured to be at 7.41, the pH that is. Okay, and so again, if we have to calculate pOH and all these and the concentrations, what I already know and what I've been given from the problem was the pH, 7.41. Now, we can find the pOH very easily. We just did it in exercise 8. So let's do it again. Take 14 and subtract that from the pH, and that will give us our pOH. Okay, now we've got pH and pOH, and a couple of these other equations. For example, the negative log of the hydrogen concentration. Now, in this particular formula, you guys know the pH, you know this. So how can you rearrange this problem to solve for the concentration? Okay, so what is the inverse function of a negative log? Well, on your calculator, you're going to want to hit the second button, if you're working on a Texas Instrument, that is. And then you're going to hit log. Okay, and what that's going to do is it's going to bring a base of 10 with a box in it. Now, to solve for hydrogen ion concentration, if you already know pH, which was 7.41, what you're going to do to solve for the hydrogen ion concentration, to do the inverse function of negative log, you would raise it to the negative pH, so 7.41. Okay, that's how you would rearrange that equation and solve for H+. And when you do that, you should get 3.9 times 10 to the minus 8. You also know the pOH, again, negative log of hydroxide concentration. To solve for OH, because you know the pOH, you would simply, again, on your calculator, take second button, hit log, you'll bring up a base of 10, and you're going to take it to the negative 6.59, raise it to the 6.59. On your calculator, when you calculate that, you should get 2.6 times 10 to the minus 7. And so there we have it. We have pH, pOH, and the respective concentrations. Exercise 10. Calculate the pH of, it looks like, 0.1 molar HNO3. Easy enough. We're given the concentration of this acid. HNO3 would be an acid, right? Because it's going to break apart into its hydrogen ions and its nitrate anions. And it's that hydrogen here that is going to be, that's the acidic hydrogen, okay? So again, pH equals the negative log of the concentration you've been given. And once you enter that in, you will see that that solution has a pH of 1. Pretty simple there. Now it wants us to calculate the pH of another acid. You can see hydrochloric, it's a strong acid. It's going to completely disassociate, leaving in solution that acidic hydrogen. All right, and again, follow the same thing you did just before, and you should get a pH of 10. So this one would be pretty basic, okay, alkaline. Last but not least, exercise 11 wants us to calculate the pH when they give us the concentration of the base. And how do I know it's a base? This is a strong base. It's going to break apart into sodium cations and hydroxide ions. And there's that hydroxide ion that contributes to alkalinity, right? Okay, and so again, if I am given the I'm giving the concentration of OH, so I can find the pOH using that concentration. So it's 1.30. This is the pOH, and I hope you guys know why I used pOH. That's because the example problem is using a base, sodium hydroxide. All right, so I found its pOH to be 1.3. And now I can subtract that number from 14 to learn and get the pH, to glean what the pH is. So it's 12.70. All right, and that is certainly a basic solution, which would make sense because we're dealing with a base. But that is going to be it for now. So thank you so much for